Okay, thank you. Yeah, hi everybody. So we've been hearing a lot the last several days about the hot gas around elliptical galaxies as an important component of the galaxies and as potentially important for quenching and quiescence. So in this talk, Greg asked me to give sort of a brief overview of the hot gas around galaxies, which is a really large topic. So I'm going to have to only, which I won't be able to cover in 20 minutes. I want to basically just touch on a few brief points here. First, I'll give a very brief and summary of what I think are a few interesting properties of hot halos that are worth thinking about in this context. I want to talk a little bit about why elliptical galaxies have hot gaseous halos, which I think is sort of an awkward question. And then I want to show some results trying to connect hot halos on different scales that are relevant for quenching here. So first I'll go quickly through some basic properties of hot halos around galaxies. This is a plot from a paper that we did last year, which basically just quantifies something that I think everybody knows. Ellipticals seem to have higher X-ray luminosity in their hot halos than spirals do. One thing that's interesting, though, is that I don't think we really know why this is. Obviously, it could be because of morphology. Ellipticals heat up their ISMs, so they have their whole ISM in the hot phase, which would explain why you see higher X-ray luminosities. But at the moment, the data are still also consistent with more boring explanations, like there being a very steep relation between the X-ray luminosity of the hot halo and either the stellar mass or the halo mass of the host galaxy. Ellipticals have higher mass-light ratios and live in more massive halos for given stellar luminosity. So both of those could, in theory, also explain this. I won't talk too much about the mass of the hot halos, but I want to just mention it briefly. These results here, by the way, come from stacking analysis of about 2,000 isolated galaxies where we stack the ROSAT data for them in order to estimate average parameters. And these are roughly L-star-sized elliptical galaxies. So for the ellipticals here, this is sort of an average estimate of the amount of hot gas that you have within 50 kiloparsecs. There's a lot of statistical and systematic uncertainties here, but a few times 10 to the 9 solar masses, I think, is a pretty reasonable estimate for the amount of hot gas we're talking about for L-star galaxies. I have to put in one slide about the total baryon budget because it's something I'm interested in. This question of missing baryons around ellipticals, there have been a few claims in recent years that some L-star or 2 L-star ellipticals can actually have all their missing baryons in the hot phase shining at X-rays. We don't think this is true. One of the galaxies that this was claimed for is NGC 720, which is a 2 times L-star elliptical. So we did an in-depth analysis of this galaxy over the last year or so. Here's its surface brightness profile, and these 3 different shaded regions are for our attempts to predict the surface brightness profiles for the different density profiles people have estimated. Ours is the red one, and you can see the surface brightness profile is fairly well behaved out to fairly large radii where it gets kind of messy. The total inferred mass in the hot halo with it enclosed as a function of radius is shown in these plots here. You can see there's a small systematic offset, a factor of 2 or so, at all radii. The other important point, though, is that our radius at which we can detect the hot gas cuts off here. The virial radius is over here, so there's this huge extrapolation. So we still don't really know, but as far as we can tell, the profile is either continuing along the power law or even steepening. So we don't think that you're going to get a lot more hot gas at large radii than the extrapolations predict. Another really relevant thing is the temperature profiles of the hot gas, which encode the feedback history of the galaxy into the hot gas around it. This plot has been around for a long time, but I don't think it's gotten as much attention as it deserves. I think it's really interesting. And the way I interpret it is also not quite the way the authors interpret it. But what we have here are about 36 temperature profiles for elliptical galaxies, measured with Chandra and colored by the average temperature of the hot gas. So you can see that for the most massive systems, which have temperatures corresponding roughly to galaxy groups, you see a pretty standard galaxy group cool core profile, temperature which declines, and then asymptotes in the core. For Milky Way mass galaxies, you have sort of the opposite. You have an inverted profile where you start near the zero temperature of the galaxy, and then once you get within the effective radius, you heat up by about a factor of 2. And this is probably due to the various feedback effects from within the galaxy heating up the gas. Yeah?
How would this plot look like if you separated galaxies based on environment, so clustered or fused galaxies versus filled galaxies?
Right. So the authors of this paper interpret the effect of the outer, they split it into inner logarithmic slope and outer logarithmic slope. And they find that the environment is a big driver of the outer slope here. So the more massive things are in bigger halos. Which is also relevant, but I think that's actually sort of saying the same thing here. Because the more massive ones being larger halos is also related to their mass. And then the intermediate objects have pretty flat profiles, which seems to me to be heating, sort of balancing cooling here. I don't want people to get the impression, though, that just because we can say broad statements about the hot gas, that the hot gas is in any way regular or uniform around these sorts of galaxies. So this is one of the many plots comparing the stellar luminosity of elliptical galaxies to the X-ray luminosity of the hot gas. This one compares field galaxies and cluster galaxies. There's a lot of different sorts of these plots, but I think this is one of the better ones. You can see that in general, as the luminosity of the galaxy gets larger, the X-ray luminosity also gets larger and it increases steeply. But what's really important here is that the scatter is really large. So, for example, at 10 to the 11th low luminosities, one galaxy might have an X-ray luminosity of 10 to the 41 in hot gas, another might be below 10 to the 38. So the point here is that there is some sort of relation, but the hot gas properties of elliptical galaxies are extremely diverse, and you can't say general statements about all of them, at least without understanding the scatter a bit. So there's been a lot of debate about what causes this huge scatter. People talk about feedback, galactic dynamics environment. Before I think we can get to that, I want to take a digression and ask why ellipticals have hot gas halos in the first place. I think this is sort of an embarrassing question to ask, but I don't think we really know precisely what the answer is. And if I'm wrong, please correct me. But as far as I can identify it, there's sort of 4 different possible reasons, and all of them seem true to some degree. So in the 1970s, sort of the 2 major things people argued about were this dynamical heating, where the motions of the stars heat up the gas, and then supernova add the extra boost of energy to make the whole ISM hot. That competes with hot mode accretion. Ellipticals live in massive halos, so they're expected to accrete hot gas in the first place. More recently, we've been talking at this conference and in some of these other papers about how AGN feedback itself might be sufficient to totally heat up the ISM or destroy it. And then finally, of course, if an elliptical galaxy lives in a cluster, the cluster is going to strip out all or some of the cold gas, maybe not in every case, and replace it with hot gas. So there's a lot of different theories for why ellipticals have hot gaseous halos. And I don't really know to what degree each of these matters. I want to show a few slides showing some of the basic data about this, but this is basically just to show a few interesting results about it. I don't really have an answer. So the metallicities of the hot gas are typically supersolar and increasing as you get closer to the galaxy. This leads people to believe, I think, that the hot gas we see came from the ISM of the galaxy because it's been enriched so highly. But as Rob Crane and Yob Shea pointed out recently, it's totally possible to have different components of hot gas. Because the emissivity of the gas depends on the metallicity, higher metallicity gas emits more. It's still possible to have the super enriched gas that came from the ISM, as well as a low metallicity, really diffuse component that came from the IGN.
So this is somehow an emission measure weighted metallicity then?
Exactly, yeah, it has to be, for simple observations at least. There's also some evidence that the dynamics of the galaxy seem to matter, which also lends support to this dynamical heating idea. So if you look at the scatter of galaxies around the LX-OK relation, slow rotators seem to lie roughly along the relation. The faster rotators scatter below it, which gives some evidence that it's the velocity dispersion of the galaxy which is also helping to heat up the hot gas halo. Environment could also be important, and I'll come back to that a little bit later in the talk. Okay, so for the next part of the talk, I want to show some new work I've been doing trying to connect galaxies, galaxy groups, and galaxy clusters, and the hot gas properties across that whole range. So the Planck collaboration last year put together this fantastic catalog of what they called locally brightest galaxies. It's about 250,000 galaxies that are selected from Sloan, and the selection criteria are basically intended to select central galaxies. So the galaxy has to be brighter than anything else within 1 projected megaparsec in radius and 1,000 kilometers per second. There's a few other criteria, and they've done comparisons with Millennium to show that most of these things are centrals and that the failure modes are pretty well understood. This is what the sample looks like. In their analysis, they split them in stellar mass in 20 logarithmic bins, so I'm going to copy that here. So you can see that the highest stellar mass bins correspond to brightest cluster galaxies, and then here you have galaxy groups, Milky Way sized galaxies where you have 20,000 or more per bin. And then once you get down to these lower things here, the numbers drop mostly because there aren't too many centrals that are detectable with Sloan at these lower masses. The redshifts are pretty low redshift, typically 0.1 or 0.2, but for the highest mass objects it gets up to 0.3 or so. The Planck team put this together because they wanted to stack these galaxies in the SZ signal, and they have this interesting plot showing the integrated pressure within R500 as a function of log stellar mass. And there's this kind of remarkable power law that goes all the way down to 10 to the 11.2 solar masses and stellar mass. They don't have a good plot that shows this, but they claim that the slope of this is consistent with being self-similar, which would imply that the hot gas around these galaxies obeys the same sort of relations as clusters do. So if clusters have all their hot gas in the intercluster medium and all the baryons in the intercluster medium, then presumably these galaxies would as well. I think that that's fairly controversial, and I'm not sure the data, I'm not sure how robust that result is, because the Planck beam is 5 or 10 arc minutes, and all of these galaxies, even their R500s, don't really fill that beam, so it's a fairly model-dependent result.
So wait a second. The slope is 3.
This is log stellar mass.
Okay, I see. So that basically.
Yeah, you have to do a lot of modeling to get that in the
Because the septimism is 5/3.
Right, yeah. So they don't have a plot where they converted this into halo mass,
Exactly.
they just essentially say that.
Just a claim.
Yeah.
What do you learn about missing baryons then from this?
Well, if it's true that the slope is self-similar, then that would mean that galaxy clusters, which have all the missing baryons in the hot gas, would obey the same sort of scalings as galaxies. So the galaxies would just have the same temperatures for their hot gas scaled down by some power law, and the same distribution of hot gas scaled down by some power law. So galaxies would look like clusters, but a little bit cooler. Right, but in terms of studying this hot gas, because I've already done some stacking with ROSAT data, I decided to stack the same sample of galaxies with ROSAT, which has 5 times better angular resolution than Planck does, and the X-ray scaling relations are pretty well understood, so it might be a little bit easier to interpret. So here's what the ROSAT stacks look like for 20 bins. I don't expect you to be able to read these numbers, but the slides are there. But these are the most massive halos really going down. You can see we have nice detections of X-ray emission all the way down to about here, which is roughly Milky Way size, and then a little bit of possible stuff below that. The circles correspond to our estimate for the average R500 for each of the bins, and then I just wanted to show a few sample surface brightness profiles to give you a sense of the quality of the data. So the red line here is our estimate of the shape of the PSF. For each of these bins, we have to also stack a bunch of point sources, matched in flux distribution and aperture size, in order to estimate how the PSF looks for every bin. And here, just to give a graphical impression, I plot the PSF normalized to the central value to show. So in these bins here, which are large galaxy groups, it's very clear that the X-ray emission is extended beyond the point source. For this, which is slightly larger than the Milky Way mass, You see a profile, but it could easily be a point source. So if you make the same sort of relation between Lx within R500 for galaxies, or for these systems, as a function of stellar mass, this is what you get. Thanks. So you have clusters up here, groups, and then galaxies, and then it sort of gets messy down here. But you still remarkably have a very smooth, unbroken power law until you get into this business. And that break isn't really meaningful for this conference. It's X-ray binaries. Low mass X-ray binaries are here. You start to get a lot of spiral galaxies over here. So high mass X-ray binaries are also contributing. And that's what's created this mess down there. But this is all a nice smooth power law. And these are mostly elliptical galaxies, groups and clusters up there.
Are these consistent with individual measurements?
For the most part. Although, I'll talk a little bit, once we get to the cluster regime, I'll say for the most part for now and get back to that at the end of the
What
talk.
is distribution within a bin?
Exactly, so that's the next thing we can do. The other cool thing we can do with stacking here. Oh. Okay, I'll wait. Okay, so the next thing we can do here is, because we have so many galaxies, we can do a bootstrapping analysis. So we can take each bin, randomly resample the same number of galaxies with replacements and stack those, which gives us an estimate of the intrinsic variation of the luminosities within each bin. So now I have two sets of error bars. They don't show up that well. The thick error bars are the measurement errors. These thin error bars here are the bootstrapping errors that show the 1 sigma variations within 100 bootstraps. You can note that for these galaxies here, which is where the LXLK relation is measured, we still have orders of magnitude scattered intrinsically, which seems to match what we see for the LXLK relation in individual objects. Because what we are looking at are pretty much all centrals, I think that's basically saying that the scatter in the LXLK relation isn't driven by environment, which is, I think, an interesting result. But it's cool that we can reproduce it. And then the scatter narrows significantly and surprisingly for the group regime and widens a bit again at the high end. I think it's widening for the high end mostly because the stellar mass to halo mass relation over here is pretty steep. So a 10 to the 11.9 solar mass BCG could be the BCG of several different kinds of clusters. So I think that's why they're scattered here, although it could also be cool core versus non-cool core clusters a bit. If we want to talk about hot gas around galaxies, then all we need to do is block out the central 0.15, 15% of R500, and then do a PSF correction to get the wings of the PSF that extend beyond that. So this is the X-ray luminosity around the galaxies between 0.15 and 1 R500. You can see it's still, there might be a break here, but I'm not sure it's very significant. And then it's pretty smooth all the way down here. And there's a pretty robust detection of circumgalactic X-ray gas all the way down to log M stars around 10 to 11, which is, I think, lower than it's usually detected. And then you can see that the intrinsic variation from the bootstrapping gets very large at that point.
And this R500, is this compared to the group R500 or the galaxy R500?
We have to compute R500 for each bin. So I didn't go into a lot into that in this talk because it's sort of a pain. But we constructed, using Millennium, a simulated catalog of galaxies using the same observational criteria as the actual ones. And we simulate, assuming a relation between the halo mass and the X-ray luminosity, an X-ray halo. We stack all those together, do aperture photometry, and use that to estimate what the effect of R500 is for each bin. I can talk with you more about that if you like. So just using the stellar mass as the x-axis here, we can fit an LX-M star relation. These are the preliminary relations. You can see we get steep slopes, we get normalizations that look pretty reasonable. Here are the effective halo masses for each bin. I'm showing just individual points here, but as I mentioned, the way we actually do the comparison is by forward modeling relations through simulated catalogs and simulating observations. This just gives you a sense of the highest bins roughly correspond to medium, smallish galaxy clusters, and then we go all the way down here. I'm only showing the
This is
12.
M500 that went into estimating R500, or this is the M500 you get out from some estimate of LX?
The one had its relations.
This is the M500 that went into estimating R500.
Okay.
So the one that we get by, this is the effective one that we're sensitive to, assuming our best fit LM relation. And then here's our best fit LM relation. So we find that we can fit a single LM relation across the whole range of the upper 12 data points before we get broken down by X-ray binaries. So it's been known for galaxy clusters that the slope of this LM relation is steeper than the self-similar prediction of 4/3. We find the same sort of thing for our relation here. 1.7, 1.8 seems to be about the slope. The normalization for our relation is about a factor of 2 or 2.5 lower than the normalization for clusters, though, which I'm a little bit uncomfortable with and still trying to understand. We think it's probably related to the fact that our catalog is optically selected instead of X-ray selected. But I'd be happy to talk more about that as well. So here's just what a self-similar relation would look like compared to data, and here's what our actual best fit power law looks like. So it looks bumpy because the power law is in the M halo, and then we forward modeled it through a simulated catalog to get estimated predictions for the data. But time's out, so I'll put up my conclusions, and thank you.
Questions, Joe, and then Krista.
So, awesome plot.
Oh, thanks.
Yeah, really impressive how much sensitivity you have. Can you say something about comparing SZ to X-ray? I realize that, this is fairly preliminary, but I mean, naively, the one is emission measure and is very sensitive to metallicity.
Yeah.
The other is just pressure and is insensitive to metallicity. So what do you learn from that?
So if the SZ result is true and it's self-similar in SZ and steeper than self-similar in X-rays, there's a few ways to reconcile it. The simplest one would just be to change the density profile systematically with function of mass. So if you're flattening out the density profile as you get to lower masses, then you can reconcile these results straightforwardly that way, which would make sense from some sort of feedback. But you can also play with temperatures as well, or metallicities.
Krista. So this was exactly my question. If you have the X-ray as X stacks, you can back out a temperature. And basically, is that one consistent with the M200 or M500 that you achieved there?
We haven't checked that yet. That would be
Because that's
interesting
a
to do.
self-consistent check, whether, especially it's important if you are finding lower normalization to see whether something is sort of out there.
Okay, yeah, that's a good suggestion. Thanks. I'll take a look at that.
Quick question from Joop, and then I think we have to move on.
What about the HT relation?
We can't measure temperatures here. So the only way we can get a temperature is by assuming a temperature mass relation and backing it out that way.
You could try hardness ratios.
Yeah, why can't you?
You can do hardness ratio with Rosetta.
We could maybe do a hardness ratio, although
And Rosetta is very sensitive to temperature changes.
it isn't with the higher masses systems, but the hardness ratio is going to be kind of tricky outside of. So I guess it would be possible at these systems, but we're pretty background dominated over here. So it's worth trying, I guess, but I'm not sure what we'll get out of it.
All right. Let's thank Mike again.